All right, still in Chapter 6, Unit 1, AP Stat. Basically, this is a good review, good practice of how to use a calculator with those normal models. Basically, how do we find the percents? How do we use normal CDF? How do we use normal inverse, the inverse norm, sorry, on the calculator to find the stuff when they give you percents? So the point is, again, these problems are long, but they're great practice to see if you know how to do them or not, so whether you write them down or not. But if I'm moving too fast, you need to pause the video to write the stuff down so that you can see the answers. But anyway, you got the tire manufacturer who believes that the tread life of its snow tires can be described by a normal model. Sweet, I know that it's normal. With a mean of 32,000, standard deviation of 2,500. If you buy a set of these tires, would it be reasonable for you to hope they'll last 40,000 miles, is the point. And explain your reasoning why. And then it says approximate what fraction of these tires can be expected to last less than. So they're talking about fractions, which means maybe they're talking about percentages that we can calculate. Approximate what fraction of these tires can be expected to last between there and there. Again, they're talking about percentages, so maybe we can figure out the fraction from the percent. Estimate the interquartile range as well. We can find the low 0.25, then the 70.75, and find the difference. And then in planning a marketing strategy, a local tire dealer wants to offer a refund whose tires fail to last a certain number of miles. However, the dealer does not want to take too big a risk. So if the dealer is willing to give refunds to no more than 1 out of every 25 customers, for what mileage can we guarantee that? So let's take a look at this. A tread life of 40,000 miles is 3.2 standard deviations above the mean, right? If you want to hope they last at least 40 miles, right? So if we wanted to figure that out, where would that be? Exactly. What you would do is you could go to inverse. You would go to normal CDF. Press that in there, and it says if you want to set up these tires, would it be reasonable if you hope they'll last 40,000 miles? Right. So if you want to figure out how many standard deviations that is above the mean, basically you could plug it in with the 40,000, or we could even go from low to high. You could go with something like negative 100,000 to 40,000 to figure out what that happens to be standard deviation wise. But we could just technically plug it in, because I could just do 40,000, figure out what that z-score is to be helpful, minus the 32,000 divided by the 2,500, and I get the 3.2. They're talking about just finding the z-score anyway on my own, because the z-score is technically the standard deviations. And then it says, according to the normal model, only approximately 0.7% of the tires are expected to have a tread life greater than that. And you could get that by saying second vars, you go to your normal CDF, and you go 40,000, comma, and then you could just plug in like something like a million, or whatever it happens to be, comma, 32,000, comma, 2,500, and you end up getting approximately 0.07% of the tires are expected. So it would not be reasonable to hope that your tires last that long, is the point. From the last that long, I'd have to be close to 7%. So then it says, and then you can see it from the picture here if I put that there and over. So I found the z-score, and I found that. And remember, anything over 3 standard deviations is really unusual. Anything over 2 standard deviations is just unusual. So the point being is that's kind of why that would not make sense. Part B, however, says approximate what fraction, and fractions are basically percents of these tires that can be expected to last less than that. So less than that. So if we were going like second vars, if I went normal CDF, negative whatever, negative 10,000 or something absurd, because it's basically, remember, it never ends, it goes to negative infinity, comma, we wanted to go 30,000, 1 2 3, with the 32,000 as the mean and the standard deviation, and I get approximately 21.186% of them should last between there. So are expected to have a tread life less than 30%, so not very many. So what fraction is basically saying what percent, right? Fractions are percents. Part C says approximate what fraction of these tires can be between 30 and 35. So between 30 and 35, because I want to know that percent, that's easy. Normal CDF, between 30,000, comma, 35,000, comma, the mean is 32,000, comma, standard deviation is 2,500, and I do get the 67.307 when I plug it into my normal CDF. So according to the model, approximately 67.31% of tires are expected to last between 30 and 35,000 miles. Estimate the interquartile range. Now I'm working the other way around. I need to find the second vars. I go to inverse norm with this, 0.25, comma, 32,000 is the mean, comma, 2,500. And when I do, I get the 30,313.76, but now I need to do it for 0.75. So I do second vars, I do inverse norm, 0.75, comma, 32,000, comma, 2,500, and I end up getting 33,686.22 as well. And when we subtract them, I get 3372.46 is my interquartile range as well. And in planning a marketing strategy, a local tire company, we said, wants to see what the risks would be, basically. It says, if the dealer is willing to give refunds to no more than 1 out of every 25, right? And trying to figure that out. Well, 1 out of 25, if I take 1 divided by 25, is 0.4%. That means the max he wants to give a refund to is the 0.4% people. So the point is, what he's saying is he takes that, now that he knows the low number, and he goes, because he knows the percentage, second vars, inverse norm, 0.04, comma, the 32,000, comma, 2,500, and when he does, he gets roughly 27,600 and 23.28, and that is basically what they're saying. So according to the model, 1 out of every 25 tires are expected to last less than that. So if the dealer is looking for a round number for a guarantee, maybe around the 27,000 miles would be a good tread life. If it doesn't work, then you get a refund if it hasn't lasted 27,000. That's basically the point. Companies that design furniture for elementary school classrooms produce a variety of sizes for kids of different ages, and suppose the heights of kindergarten children can be described by this normal model, with the mean of 38.2, standard deviation of 1.8. The key there was normal model. What fraction, when they're talking about fractions, they're talking about percents, of kindergarten kids should the company expect to be less than 3 feet tall? So when we're looking at this, 3 feet tall, if this is done in inches, I need to switch it. So 3 feet tall is 36 inches. So basically when we're doing this, if I want to find that percent from low, no one would be lower than 0, but anyway, you put in like negative 10 inches, comma, 36, comma, 38.2, comma, 1.8, and you'll get 11.1%. And so basically around 11.1% of them. B, it says, in what height interval should the company expect to find the middle 80? So if that's the middle, all right, right here, that's 40% on either side. So if that's 50, 40%, so that means I want 0.1, and I want 0.9, because that's 50 and 40 is 90. So 0.1, 0.9, so I would do inverse norm of 0.1, comma, 38.2, comma, 1.8, it would give me this. And if I did inverse norm of 0.9, comma, 38.2, comma, 38.2, comma, 1.8, and now I'm looking at the middle numbers there, so it says between those two numbers would end up being my heights, where the middle 80% would be. And then, at least how tall are the biggest 10% of kindergartners? So this is just me writing down that the middle 80% of kindergartners are expected to be between 35.89 and 40.51 inches tall. So if they wanted the Z-scores to do that as well. Okay. To do C, though, it says at least how tall are the biggest 10%. So I want the biggest 10, which means I want 0.9. And if I do that, it would be 0.9, inverse norm 0.9, 38.2, 1.8, and I would get what that number is as the percent, which is 40.51. So the tallest 10% of kindergartners are expected to be at least 40.51 inches tall. Alright, looking through this one here, trying to finish up in one video. As you read through this, to summarize, it says they're doing a report. Researchers report that the more accurate figure may be 98.2 degrees Fahrenheit, because it says most people think that the normal adult body temperature is 98.6, but research has shown that maybe it's 98.2. Standard deviation appeared to be around 0.7. Assume the normal model. In what interval would you expect most people's body temperature to be? So looking at this, according to the normal model, 95% of people's body temperatures are expected to be between this. And the reason why is because if that's what they're expecting, you basically could add one standard deviation to it, add another standard deviation to it, or subtract and subtract as well to get your intervals of 95% and 99%. So it says virtually all people are expected to be between this anyway. So it says, in what interval would you expect most people? Well, most people are definitely there. Almost all are between 96 and 99.6. It says what fraction of people, and that's with the normal model if we use that. And then it says what fraction of people would be expected to have body temperatures above 98.6. So basically we would do what percent. That means if I'm trying to find the percent and I don't know it, I would do normal CDF, 98.6, like 1,000. 98.2, 0.7, and it would give me the 28.39%. And then it says what body temperature are the coolest 20% of people. Well, now if I'm giving the percent and I want to find that number, in order to do this, below what body temp are the coolest 20? So now it's inverse norm 0.2, 98.2, 0.7. And I would end up getting 97.61 with that as well. Alright, I'm not able to quite finish it all up, but hopefully we can finish this up maybe when we come back.